Hi guys, in continuation of our motor control series, today we'll be talking about VFD, which generally it's called the inverter, and another name for VFD is VSD, and another name they call it is drives. What's the full meaning of VFD? The full meaning of VFD is variable frequency drive, and it's also called VSD, which means variable speed drives. What's the function of a VFD? As the name implies, the function is to regulate or variate the speed of a drive of a motor. In the motor control series, we can only start or stop or change the direction of our electric motor. So in order to change the speed, we must be able to regulate the speed in a situation whereby we won't have much power loss. Now we have three major components of electrical energy, which is of an alternating AC electrical energy, which is the power, which is the voltage, frequency, and current. And what VFD basically does is to variate the frequency of the power supply to the induction motor. And we all know that frequency is the rate of change of the polarity of an AC signal from the positive half cycle to the negative half cycle. I will try as much as possible to keep this series as simple as possible, so I will not speak much of the technicalities that is involved in the operation of an induction motor. So what VFD works by taking in the AC signal, because we can't step up or step down DC voltage. At the same time, DC voltage doesn't have frequency because it's a direct voltage. So in order to be able to change the frequency of a signal, we have to select the best time to change this frequency, and the best time is during the process of inversion from DC to AC. So basically how VFD works is VFD takes in AC signal or an already rectified DC signal and then convert it to AC, which technically is called inversion. So during the process of this inversion, the system, based on the preset settings, can alter the frequency of inversion, and by so doing alter the frequency that is supplied to the electric motor. What I'm saying basically is VFD takes in either AC or DC depending on the VFD on the available power supply, and invert it back to AC. Inversion is the process of converting DC signal to AC. Now during this process of inversion, the speed of inversion, which is the frequency, which is the number of time is inverted in a second, can be altered. Now how does VFD convert DC to AC? It does this by using switching circuits. This is more of electronic circuit. It can be done using power transistors like a BJT, MOSFET, or SCR. But basically in VFD, SCR is the most appropriate because of you want 100% energy conversion. At times, IGBT, insulated gate bipolar transistor, are used too, and it's either SCR or IGBT for the design of VFD. So IGBT are switch, they are solid state switch that are used to switch a signal. So it depends on, depending on what you want to do. IGBT switching is the best method for VFD voltage inversion. So there is a microcontroller inside the VFD that is responsible for switching the series of IGBTs. We have the configuration of the IGBT is H-bridge configuration. What I mean by the configuration is the method by which the IGBT is arranged in order to switch from positive to negative during each half cycle. So VFD works, like I said, by taking in AC or DC and inverting it back to AC, thereby altering the frequency. So enough of my theory. I try as much as possible to keep the theory to the barest minimum. So in this circuit above, Starting from our source, we have a three-phase power supply, so we use a 400 volt DC, 400 volt AC. Now you can see from our indicator here, we have 399.94 volt AC. Now, and our frequency, this is our frequency meter, and this is the input of our VFD. That means our VFD takes in three-phase input. Now, this is the output of our VFD, U, V, and W, that is directly connected to our electric motor. Now, our VFD, we have a start circuit, stop circuit, forward circuit, reverse circuit, and the speed circuit. So now let me walk you through the circuit. These are stop circuit. Depending on the manufacturer of your VFD, everything has its own configuration. This VFD is I think it's Allen Bradley VFD, and it is configured according to the owner's manual and instruction manual by the manufacturer. So our stop signal is going to port 0, our start signal is going to port 2, and our reverse signal is going to port 3. And remember, it depends how are we connecting. We might decide to sync or source our power supply. Now, our control circuit or VFD, all these things will be explained inside the owner's manual. I won't be specific on this because there are various brands and manufacturers of VFD, and all the configuration varies. Now, for our speed control, we have two objects of control. You can control by regulating the current to a particular input or regulating the voltage. In this tutorial, we'll be using current control, current regulation. And by regulating, how are we able to achieve this? This is by varying our resistance. We all know that V is equal to IR. That means voltage is V is equal to IR. That means voltage is directly proportional to current and resistance. So by regulating our resistance, we can regulate the current that is going into our VFD, thereby regulating the speed. So we chose a 1000 ohms variable resistor here, POT, and it can move from 0% to 100%. 100% means 1000 ohms, 0% means 0 ohms. Now we have our push button, stop push button, like our normal direct online starter. Another advantage of VFD is we can use it for what's it called, forward and reverse control of our electric motor. Another advantage of VFD is that VFD helps to soft start our motor. That means normally when we're using direct online starter or contactor control for our motor, we don't have much power in correcting the starting current of our electric motor, and that is the reason for soft starter. So VFD also works as soft starter. That means it will allow our motors to start from 0 to the maximum RPM gradually, preventing a very huge surge of current, which we know as starting current. So VFD also helps to regulate that. So in this system, we have our power supply, and we have our power out, and we have our motor control. So we'll start this VFD this system by activating our contactor, our circuit breaker. Now breaker is on. We can see that the voltage supply to this VFD is 58. Now at the moment there is 0 current going out and there is 0 voltage going out, and the frequency at the output is also 0. So this is the indicator of our electric motor. This is the speed of our electric motor, and this is the load on our electric motor. So I will start by starting this motor in a forward bias. So I will send a forward signal to our VFD. So the forward signal, you can see our electric motor is gradually gaining its speed because VFD also works as a stop starter. And when you look at our current output here, we have 22.3 ampere output, and it's gradually reducing. Although the reduction is not much, but you can see that this is better than times 3 or times 4 of the starting current that we use in contactor control. And our voltage is 399 volt, and you can see voltage by going by voltage times current. 400 multiplied by 8 in our RMS will give you 2.279 4.8 kilowatt. Now we can change this to power. When we look at our power, reactive power is 2620 VAR, which is our, let's change it to kVAR, kilowatt. That's 2.6 kilowatt. I think we all understand the difference between apparent energy, apparent power and reactive power. So let's change this to apparent power. You can see it's 3.2 3220 VO. Going to kilovar, we have 3.2 kVAR. Now let's check for our real. Okay, I think we don't have opportunity of seeing our real power here. Nevertheless, our real power is 4.8 kilowatt according to active power, good, which is the same thing as real power. Let's change to kilowatt and see our motor is consuming where it's demanding for 1.9 kilowatt from the source. So let's go to the reverse direction and see. We'll stop. Our circuit has been stopped and you can see the speed of our electric motor gradually going back to 0. So once it gets to 0, we can start in the reverse direction. You can see the arrow showing that our motor is currently working in the reverse direction, and you can see the frequency of our motor is on 80 Hz, and the frequency input here is 50 Hz. Let me go back to voltage, RMS voltage, so that you can see, since this is already displaying our power. Now this is our voltage, 399 volts, and our current is 8 amps. So the maximum speed, so we can see the speed of electric motor is 2279 rpm, revolutions per minute, and our frequency now is 80 Hz. So because the settings of our variable resistor is already at 100%, we can gradually go back to 50%. When we're on 50%, you can see the frequency of our motor. The frequency of the VFD supply motor is 40 Hz. Nevertheless, the input frequency is 50 Hz, but our VFD is able to supply 40 Hz at 200 volts. Now, people might ask me why the change in voltage. Yes, because the VFD works by sending pulse signal, pulse width modulation to the gate of our IGBT of our MOSFET. Now, and this is done by regulating the duty cycle. A lower duty cycle will produce a low voltage and a low frequency, and that's the reason we're having a low voltage output and a low frequency based on our set point here. So what our resistor basically is doing is to regulate the pulse, the duty cycle of our PWM switching to our IGBT. So this is more of electronics, so we won't dwell much on that. So let's reduce our speed furthermore to a point. So our speed is so low now, and if it's so low that our electric motor cannot start even though there is power. So we can see we only have 30 volts, so we can increase a bit and see. Let's go now. We've been able to increase our speed, but still we can't achieve much. So I think it's better we go to in this settings. I think the minimum frequency that our motor can use is 50. It's at 50%. That's 500 ohms, and I think the frequency is 40 Hz. Please go along with me. Please do well to follow whatever I'm saying. I think I might. I didn't practice this before doing this video. I want it to be as real and as realistic as possible. So pardon my the alterations in my data. We can always check this and see this together. So we can see we're on 199.9 volts and we are on 8.03 amps. But our voltage from the source remains the same, and our motor is already running in a reverse direction. So by increasing this, you can see we're already increasing our frequency. Increasing our frequency means increased in the RPM, at the same time in our voltage, which means our power will increase. So let's go to 100%, which is 80 Hz, and our motor is gradually gaining speed. So this is a simple illustration of how variable frequency drives work, or variable speed drives, or inverters, or drives, depending on what we're using them. Thank you and God bless.